When we have a simple digital system that requires few logic gates, it is convenient to place all the code into one file. But as the system grows or the complexity of the circuit increases, it is more efficient to break the huge code into groups of external files and just access these files from a one main file. What we're doing here is modular programming. Modular programming is the process of subdividing a huge computer program into separate subprograms or modules. Generally, programs are easier to code in a modular approach because smaller pieces of statement blocks are easier to design. It is also easier to debug many individual modules than debugging one huge code file with multiple functions. More importantly, in modular programming, one module with a specific function or routine can be reused by other modules. To demonstrate modular programming, we will construct a 3-bit synchronous counter. Let's represent the 3 bits as the outputs of the toggle flip-flops. For the lowest bit position of the counter output, we have Q sub 0. And for the second bit, we have Q sub 1. And for the third bit, with binary weight of decimal 4, we have Q sub 2. Since this is a synchronous counter, each flip-flop is updated simultaneously by a clock pulse. Therefore, let's connect each clock input to a common input pulse, which we label as CLK for clock pulse. So initially, the counter starts counting from 0, 0, 0, but during the middle of the counting, we can force the counter to return counting from 0 by activating these clear inputs. To simultaneously change all the bits to logic 0, we connect the clear inputs to a common connection which we call as reset. Based on this setup, if we want to clear the bits, we have to supply the reset signal with logic 0 since clear here has a bubble sign, which means that this is activated for logic 0. But if we want the counter to reset at logic 1, then we have to add a NOT gate here at this reset signal. If you will perform the procedure for constructing a sequential circuit which involves K-map, you will find out that the flip-flop for Q sub 0 must be connected to logic 1. Of course, the connections of Q sub 0, Q sub 1, and Q sub 2 that I'm about to show you will be different for other number of bits like 4-bit synchronous counter, 8-bit synchronous counter, and so on. For the input T sub 1 of the flip-flop, based on K-map, this will depend on the output Q sub 0. That's why there's a direct connection from Q sub 0 to the input T sub 1. Finally, the output Q sub 2 based on K-map depends on Q sub 0 and Q sub 1, and these inputs are AND together before connecting to input T sub 2. So let's implement this 3-bit synchronous counter using modular approach. To construct this 3-bit synchronous counter using modular approach, we will just create a module for the T flip-flop, then reuse this one module to reconstruct these 3 individual flip-flops in a main file. So click New Text File, select a language, scroll down, choose Verilog. So this would be our module for a one toggle flip-flop. Save this file. So let's name this file as t underscore flip-flop.v. Again, the file name is important when accessing it by other modules or the test bench. We will not be using built-in libraries for the flip-flop from Verilog. We will create our own flip-flop module. In other words, this module is defined by us. Hence, this module is user-defined or it is a user-defined module. Let's type module and module. We will place all the code for this T flip-flop between this module and end module keywords. So let's name this module as T underscore flip-flop. The name of the module is important, especially when we create a copy of this module or an instance of this module during simulation. So based on this diagram, the T flip-flop must have input ports for T input. So I'll just name this variable as t underscore in to remind us that this is an input port. The same goes for the clock input. And the same goes to the reset input. Also, based on this diagram, the flip-flop must have an output Q. I'm going to write it as Q sub out to remind us that this variable is an output. Let me terminate it with a semicolon. Now, I'm going to include a keyword reg here so that this Q out variable can store binary values along the way. So based on the diagram also, we need to update the value of Q for every negative edge of the clock pulse. That's what the bubble signifies here. Inside this always block that is triggered by the negative edge of a clock pulse, we update Q to 0 when reset input is logic high. Since I will be feeding this with 1 bit, because this flip-flop input is only 1 bit, I'll type 1, referring to the size of 1 bit, apostrophe B, then a value of 0. Otherwise, we toggle the value of Q when T input of the flip-flop is logic high. Else, we retain the value of the output Q. In other words, the output Q is not toggled. This is our module for T flip-flop, and we will be using this when constructing this 3-bit synchronous counter. Let's open a new Verilog file. So select a language, Verilog, and save it as sync underscore counter.v. So this would be our module for this 3-bit synchronous counter. Again, it is saved in the file sync underscore counter.v. Now, this is where modular programming takes place. In fact, we have been using it when we code test benches, especially that when we want to separate the code to be tested to that test bench code. To access the T flip-flop module, this one that we made earlier, we simply type the compiler directive grave accent include, then the name of the module to be included, which in our case, this is T underscore flip-flop.v. So this line of code here is similar to cutting and paste all the code in this T flip-flop module to our current file, which is sync underscore counter.v. So let's now construct this 3-bit synchronous counter by typing the keywords module and module. So we will place all the Verilog code for the counter between these keywords module and end module. Let's name this module as sync underscore counter. I can write this as 3-bit synchronous counter, but this will not be allowed in Verilog because it starts with a number. So that's why I'll stick with synchronous counter. This name of the module is important when we instantiate the counter in a test bench for testing. So going back to this diagram, if we will enclose this circuit diagram with a box, you will notice that our counter must have inputs for receiving clock pulses and reset signal. Also, I have to create this output bits, which we will name as Q. And then its size will be 3 bits with index from 2 to 1, then 1 to 0. Here, I did not include underscore in for the inputs, nor underscore out for the output, because I want to shorten the variable names. So let's now build the circuit by first creating an instance of the flip-flops. Let's create this first flip-flop with index 0. Remember our user-defined module T flip-flop, this one. So let's create one instance of such flip-flop, and let's name it as TFF0 to refer to this flip-flop with index of 0. Now going back to the arrangement of input and output ports in this module, first we must have T input, And based on this diagram, this T input must be connected to a logic 1. Next, let's go back here. We need to have a clock input and reset input. So I'll just copy this clock input here and reset input here. Let's go back to this module. For the flip-flop output, we place Q sub 0 here. Let's now instantiate the second flip-flop. For the second flip-flop with index 1, let's create an instance of such flip-flop and just name it as TFF1. Using the above instance as a guide for the ordering of ports, first we must have T input. But based on this diagram, T sub 1 must be connected to Q sub 0. So I'll put Q sub 0 here. Next would be our clock. Next would be our reset. And finally, for the flip-flop output, we must access this Q sub 1 output. Hence, we place Q sub 1 here. Okay. For the third flip-flop with index 2, let's create an instance of such flip-flop and just name it as TFF2. Using the above instance as guide for the ordering of ports, first we must have T input, but based on the diagram, it is connected to an AND gate, and this AND gate depends on Q sub 0 and Q sub 1. Hence, we need to instantiate an AND gate, and let's just name it as A sub 1. For its output, let's create a wire. And let's name this wire as T sub 2 for the toggle flip-flop 2 input connection. So we use this wire as the output of this AND gate. Then use Q of 0 and Q of 1 for the input of this AND gate. Then we use this wire T sub 2 as the input for TFF2. Then we connect the clock input, then the reset input. Also, based on this diagram, the output of this flip-flop is Q of 2. So that's it. All we have to do is test this counter if it's working. So click File, New Text File, select a language, choose Verilog, and let's save this as Synchronous Counter _TB to denote that this file is a testbench.v for Verilog. So again, this is our test bench for our 3-bit synchronous counter, and we've given it with the file name of synchronous counter testbench.v. Let me set the division of our time scale as 1 nanosecond. So type in grave accent, time scale, 1 nanosecond, 1 nanosecond. Let's include the code to be tested using this compiler directive grave accent include, then the name of the file to be tested, which is sync counter.v. So let's now write our test bench module by typing the keyword module and also end module. Between these keywords are the statements for our test bench. Let me name this test bench as synchronous counter test bench. This module doesn't have inputs and outputs, so I'll end this with a semicolon. So to change the input signals and output signals of our synchronous counter, let me create variables whose signals will be fed to our counter. First, let's create registers that will store the clock pulse inputs and reset inputs. I included the underscore in the variable name so that when we print the timing diagram, we can easily discern which signal is an input and which one is not. Also, let's create a wire Q sub out that will store the output signals of the counter. This output will have indices from 2 to 1, then 1 to 0. So let's create a copy or an instance of our counter. Let's go back to our module. Remember the name of our module. Let's copy this name and paste it here. Let's name our instance as, for example, Synchronous Counter 1 or SC1. Based on this module, it must have a connection for the clock pulse, the reset signal, and the output signals as an array of bits. So let's connect our test bench variables in the same order as what is shown in this declaration. So clock, then reset input, and then Q out. So before we begin feeding our counter with various input signals, let's create clock pulses. First, let's feed it with logic 1. Sorry. And then we will toggle this value using the forever keyword with an interval of 1 nanosecond. For now, these pulses will run forever, so we will just terminate this later in the code. Next, let's create another initial block that will control our counter. So after 1 nanosecond, let's equate reset input to 1 so that the counting will reset to 000. Then after 1 nanosecond, let's equate reset signal with 0 so that the counter will begin counting regularly. We let the counter count for 10 nanoseconds. Then after, let's say 1 nanosecond, let's again equate reset input to 1 so that the counting will suddenly reset back to 000. Then after 1 nanosecond, let's equate reset input signal to 0 so that the counter will resume counting for every negative edge of the clock pulse. So we let the counter count for, let's say, 20 nanoseconds and see if it automatically returns to 0 when it reaches 111. To save the changes in the outputs, let's create a dump file here. Recall that the clock pulses will execute forever. Therefore, we will forcibly stop the simulation by including a $ finish here. To compile our test bench, click this toggle panel. Go to the directory where your files are located. Let's compile the test bench by typing iverilog space -o to signify output, then the name of the compiled file. So for conciseness, let's just name it as test.vvp, and then the source file to be compiled, which is sync underscore counter underscore testbench.v. So hit enter. This must generate a test.vvp file. Now let's run this vvp file to generate a dump file. vvp, then the name of the vvp file, test.vvp. Notice that it generated this file sync underscore counter.vct. Let's open GTK Wave and check how our counter behaves. So click File, open new tab, then choose this dump file sync underscore counter.bcd, then choose this data, and then click any of the signals, then Control A, then append all these signals here. So in this timing diagram, the topmost waveform refers to output Q, the middle waveform refers to clock pulses, and this bottommost waveform refers to the reset input. Note that when we send logic high to the reset input and after 1 nanosecond revert it to logic 0, the counter starts from 000, then 1, 2, 3, and so on. Note that when the counting reaches 101, or maybe this number 5, 4, 5, it suddenly resets to 0 because remember that in the test bench, we momentarily fed the reset input with logic 1, then after 1 nanosecond, we set it again to 0. So in other words, when we momentarily fed reset input with logic 1, the counter resets to 0, 0. So from this point, the counter counts regularly, and when, for example, 0, 1, 2, 3, 4, 5, 6, 7, when it reaches 7 or 111, it automatically resumes to 0, 0, 0, and then 1, and then so on. So based on this timing diagram, our Verilog code is consistent with our 3-bit synchronous counter. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!